Okay, in the last video we looked at the kinetic energy involved in different kinds of collisions. We looked at both elastic and inelastic collisions. We looked at two different examples of inelastic collisions, one of which was a perfectly inelastic collision and the other was a bounce-off inelastic collision. Here we're going to not just look at the kinetic energy involved in this elastic collision, but we're also going to use the fact that it's elastic to be able to predict the final velocity of both objects. In all of our prior examples, and we did a lot of them, the unknown velocity, there was only one unknown velocity that we could solve for because we only had one equation, the conservation of momentum equation. But here, we're going to have two unknowns, and we're going to be able to solve for both of those unknowns because we have two equations. And so let's just say to the right is our positive x direction. Draw a little diagram up here. And we'll say we have a 10 kilogram object, and its v sub I, we'll call it v1i, is 10 meters per second. And we've got another object here. It's a 15 kilogram object. And we'll say it's moving, well, not say, it is, it's given in the problem. It's moving at 20 meters per second, and it's moving in the opposite direction. So we'll say that's negative 20 meters per second. And so this is all of the initial information here. Okay, that's our initial state. And then final is what's happening right after. So right after the collision, we've got our 10 kilogram object, and I actually don't know which way it's going. Okay, it was moving that way, and this one was moving that way. We don't really know. So V1F is an unknown, and we've got our 15 kilogram object, and V2F is also an unknown. So this is our final state. All right, so that gives us a little diagram of what's going on here. And again, if we use our conservation of momentum, it simply is going to, say that Pi equals Pf, initial momentum equals final momentum. So we could say m1 v1i plus m2 v2i, remembering that velocity is a vector, and m1 v1f plus m2 v2f. All right, now plugging in numbers, we would say, okay, 10 kilograms times 10 meters per second plus 15 kilograms times negative 20 meters per second equals 10 kilograms times v1f plus 15 kilograms v2f. And this equation has two unknowns. Okay, there's two unknowns in there, so we can't solve it. What we need is another equation. That's what we do. Okay, we can do another equation. If we look on the equation sheet, we see an equation that is only applicable for elastic collisions. Okay, and that equation is v1i minus v2i equals negative v1f, the quantity, v1f minus v2f. Okay, so now we can fill in the known value, so 10 meters per second minus negative 20 meters per second equals, and then I'm just going to distribute this negative sign, so negative v1f plus v2f and I've got two unknowns in this equation as well. And then I look and it's the same two unknowns. And that's great, because now I've got two equations and two unknowns, so I know it's solvable. And now it's just a matter of actually solving it. So I can add these together. I got 30 meters per second, so 30 meters per second plus v1f. I add v1f to both sides, and that's equal to v2f. I can then take that expression and I can plug it in right here for v2f. Pardon me. So this gives, starting with the left-hand side of this equation right here, that gives a value of, let's see, that's 100, and this is negative 300, and so that's negative 200 kilogram, sorry about that, negative 200 kilogram meters per second equals 10 kilograms. Okay, so I'm just following along right here, times V1F plus 15 kilograms times, and this is where V2F would go, but instead of V2F, I'm going to put in 30 meters per second plus V1F. And now I can do some algebra on this. So this becomes negative 2, well, that stays negative 200 meters per second equals 10 V1F plus 450 kilogram meters per second plus 15 kilograms times V1F. And so I look, now I could subtract 450 kilogram meters per second from both sides and get negative 650 kilogram meters per second on the left. I can take my 10 times V1F plus my 15 times V1F, and I get 25 kilograms times V1F. Now I divide both sides by 25 kilograms. And so V1F equals 26 meters per second. Negative 26. Negative divided by positive. That's going to get negative 26 meters per second. So that means V1F, or I'm sorry, object 1 is going to the left, and it's going to the left quite quickly after the collision. Now we're not finished because we have two unknowns. The other unknown is V2F. Well, we know V2F. Okay, we can take this and we can plug it into that equation. So now V2F equals 30 meters per second plus this value, negative 26 meters per second. And so V2F simply equals 4 meters per second. Okay, so object 2 is going to change directions. It's going to move to the right and move rather slowly after the collision. And now we can look, we should be able to verify that the kinetic energy is the same before and after the collision. So we look before the collision, we've got these objects. I'm just going to fill in for object 1, and then for object 2, it was moving at 20 meters per second. And put the negative sign there. If that makes you feel better. And we see that that is 3,500 joules. And we calculate the energy after the collision. Our 10 kilogram object is now moving at 26 meters per second. And it's in the negative direction. Not that it matters when we're doing our energy calculation, of course. And our second object moving along slowly, and we add these together and we get 3,500 joules. So yes, kinetic energy is conserved. And I know it looks a little weird, but this equation right here, that again is only for elastic collisions, and this is based on energy being conserved. And in the OpenStax textbook, as with probably most textbooks, you will find a kind of a derivation of this equation where they start with the idea that the kinetic energy is equal before and after the collision, and then they do some algebraic work to get to this equation. Actually combine it with the idea of conservation of momentum. But in any case, this is a nice simple equation that we can use. You don't have to memorize it. It is on your equation sheet. So feel free to make up your own problem and solve it. You could just change any of these initial conditions, any of these first four numbers here, and then you could solve for those final velocities, and then you can check by doing just what we did, check that the kinetic energy is equal before and after the collision.